I'm John Wilker, the organizer of 360 IDEP. I hope you enjoy this session recording, but first I wanted to mention one thing. We've served the community since 2009, and over the past few years we've had to take on debt in an effort to keep the conference alive. After several unforeseen challenges, not the least of which is a pandemic of indefinite duration, we've had to make the hard choice to end the conference as we're now facing over $100,000 in debt. As a result of requests from the community of how they can help, we've created a GoFundMe campaign. If you're inclined and able, please consider donating to help keep 360 IDEP going. The QR code after this will link you to the campaign. Thank you. Enjoy the recording.
All right, everybody. For those of you who don't know me, my name is Ben Proothi, and today we are going to be time traveling with Swift. We're going to be taking a quick look at where we are, where we started, and where we're going. Now, my thought for this talk was to kind of make a history for dummies, but like Swift edition. You know, you've all seen those YouTube videos like, this is the Civil War, but it's all cartoons, so you can understand it. That's kind of the goal here, except less cartoons and more code snippets. So first off, just before we get started, I want to go through what is Swift. Now, I know most of you are going to know this already because, again, you're iOS engineers, but I want to give some context here because, again, this is history for dummies, not history for engineers. So Swift is a powerful and intuitive programming language, blah, blah, blah. Okay, this is just all from Apple. If you want to read this, you can just like go ahead. Ready? Like go. 5, 4, okay, yeah, you got enough time with this. Better introduction to what Swift is. Swift features just a couple of key characteristics that are going to make it different from other programming languages. So my definition of Swift is something that is object-oriented, type-safe, functional, clear, and high-level. Now, just as a little bit more detail into what each one of these means, object-oriented just means that we have classes, objects. Everything in Swift is some sort of tangible object that's not actually tangible because it lives in a computer. That's why you see that class rectangle up there. All that means is we're object-oriented. Type-safe, that means that each object belongs to a certain type. The type is basically a blueprint. It says this object is, in this case, a rectangle, or it is a square, or it is more than one of those things. Like a square is both a rectangle and a square. Functional just means we have functions. See that get area method? That's a function. Clear means this is all easy to understand. Easy for you guys, hard for like 90% of the population, but we're going to ignore them and just say that this is clear and easy to understand because it kind of is. High level just means that we don't have to deal with memory management on our own. We're going to get a little deeper into that later on, but for now, high level just means that all of the behind the scenes stuff is handled by the computer, by Swift, and we don't have to worry about the nitty gritty. In other words, it just works. You know, Steve Jobs got a lot more applause when he said that, so like, let's try this again. It just works. All right, I'm done being disappointed. Let's keep going. Let's take a look at the past. Again, that's kind of the whole point of this thing. You guys can like make up sound effects on your own. We're doing this whole time travel thing, but like I'm kind of lazy and didn't want to like put the sounds in myself. This hookup stuff up here is all a mess. So make up the time travel effects on your own. Personally, I'm gonna go with like DeLorean type sounds in my head, but like you guys can do whatever you want. So just go right ahead. First off, we start with like baby Swift. This is where you have this Swift family tree. You have the godfather that is Fortran living over everything else. You have daddy Objective-C. You have your older brother TypeScript. You got that weird brother that is Kotlin. He's like not even on here because he's sort of like this black sheep of the family. I'm not sure we want to picture him at all. We kind of just don't talk about him. And then the next step with Swift was really just this internal build. Something that's really interesting about Swift specifically compared to other languages is that it started off as something that is absolutely completely different than what it now is. Swift started off, for those of you who remember from last night, as shiny, as in you're building this shiny new thing. So some of you heard this at Stomp, some of you might have known this, or you just like used Google or whatever, you know, cheating, whatever. Again, I don't really have time to be disappointed in you for using Google here, but You can just like read this quote over. I just read it to you. Either way, this was said by the great Chris Latner. Hail Chris Latner. You could come on. Hail Chris Latner. Thank you. Much better. Come on. You guys need to get better at this. I can't keep being disappointed. Come on. Anyway. High-level programming. That's what makes Swift Swift. I talked about this before, and it's really just something that completely makes Swift a step up from Objective-C. Whereas Objective-C is this low-level language, Swift is a high-level language, meaning that everything that Objective-C you have to do yourself, Swift makes easier. And again, engineers are lazy. We like this stuff. It makes our lives better. But when Objective-C is not really a fan of making our lives better, we need to kind of find a new thing to do here, and that's where Swift is born. This starts off with ARC, the automatic reference counter. Objects are, as you can see there, released from memory once there are no more references. So just to go through here, you got this parent class, which holds a reference to a child. And let's say, as you can see over here, we had this parent with a child, Dana. And now we're replacing Dana with Zool. At this point, there is no Dana, only Zool. You can try to find Dana, you can't. Keep trying, come on. No, you can't find it. Dana's not reached. Dana is lost in the oblivion. There are no ties left to Dana. And so Dana has faded from memory. Dana is no more. Don't be like Dana. Reference loops are when, even though there's no real way to find that child, in this case Dana, Dana's still around. And we have no way of getting rid of Dana or Dana's parent. When a parent and child are both holding a reference to each other, even if you delete both of them from any references, they're both going to hold a reference to each other, and so that makes it so that they are stuck in memory. You do enough of these, they build up, build up, build up, you get the straw that breaks the camel's back, your app crashes, and that's not fun. So how do we fix that? You use these things like weak var, all in these, hard brackets, whatever. Other ways of doing this are just using optional types. There's a million different ways to fix it. Swift provides us with a bunch, and that, again, makes our lives easier as engineers. The reason that Swift has all of these features is because we are bad at catching bugs. We're bad at finding these reference loops on our own. So if you can make it so that, let's say, the child does not hold the reference to the parent, life is just easier. But again, you guys know all this stuff about reference loops. You're engineers. You should know this. If you don't, I'm disappointed again. But how do we kind of manage this whole situation without having to go so deep? You just limit the use of reference types. It's an approach. I don't know if it's the best approach, but it's something. But again, we can't do that with the current state of Swift. See, Swift by now is still this piece within Objective-C. It hasn't really broken off yet. And when we try introducing this new automatic reference counter to Objective-C, we run into some problems. You see, we are able to add it only to these Cocoa APIs at first, which is going to be your UI kit, foundation. It's everything that makes your apps work. However, it really just doesn't vibe with the Objective-C stuff. Objective-C is all about low-level memory management, as you can see there. And they're really all based on these reference types. So what that means is that automatic reference counting is going to try to solve this reference type issue every time that you're creating a class in UI kit. It's going to try to be that garbage collector and make everything work, but it can't do this on its own. Automatic reference counting, Objective-C, they don't work. As you can see, when this was first implemented, you just run into a million errors. Why? It doesn't matter. It doesn't work. So we need to find a better solution. Now, what the cause of these errors is just this incompatibility between Objective-C and a high-level memory management system. Objective-C is designed in mind with the idea that you are going to be managing the memory on your own as a developer. And so you have these two very different ideologies here of low-level management, where you as an individual developer are going to deal with the memory, or high-level management, where you want the code to do it all for you. And these two different schools of thought existing within one language start to cause some small issues. And that's when you get Objective-C without the C. This saying, I'm sure you've all heard a million times, is said by Craig Federighi, aka Air Force One, aka the only 53-year-old who has hair better than myself. And so that's where you get this break-off, this speciation, as I like to call it. It's really a biology term, but I thought it was pretty fitting. The speciation is when you have two different populations, and as they are separated from each other for a long time, they are no longer able to reproduce together, and they just become two completely separate beings. And so while before you have Objective-C and Swift as these two schools of thought that kind of are contradictory, existing within one language, they're going to start to break off and form this schism that essentially will lead to it becoming so incompatible that Swift must become its own being, if you will. But enough about the biology, that's really not the point here. We now get to build our own language. Now that we have the idea of we're going to make something new, we decide, well, if we're making it new, make it better. So because we can do whatever we want, this is when we start to implement the more clear syntax. There's no more of those hard brackets absolutely everywhere within Objective-C. You're able to use this new closure syntax that just makes life easier. There are a million things that can now be done so easily just because we had the chance to erase the board and restart with something new. In addition to that, we get a full implementation of the automatic reference counting, which was not in Objective-C. Again, that was only part of the Cocoa API, and now with Swift, the automatic reference counting is just built into the language. It's part of all libraries. In addition, we get the introduction of value types. Now, in Objective-C, structs are discouraged, to say the least. Everything in Objective-C is founded on classes. You want to make a view, it's a class. You want to make a view controller, it's another class. Soon enough, you have a million classes with a million different references to each other, and handling that memory management becomes very complex. But with Swift, we now have value types that are not your only option by any stretch, but if your project is better suited for value types, you have value types. However, we have this one little issue here. Swift is still dependent on Objective-C. And now I know I said all this stuff about speciation. It shouldn't be dependent. It should be its own thing now. They should be completely separate. One small issue. Cocoa Touch. See, this is UIKit Foundation. It is everything that makes, it's everything that makes the apps work. So we need to find something to fix that because none of the apps work. All right, you know what? It's a later problem. We're gonna move on. So now we have this Gilded Age of Swift. Gilded Age kind of being another historical term where you get, it looks gold on the outside and inside it is not gold. It is something else. Now here you have Swift as this closed source controlled by Apple. And at this time, when Swift was first released, they released kind of half of what they had been working on, and they kept the rest of it internal so that they could release in increments and in a way perfect or at least improve each part of Swift before they release more. So this is when you have new features constantly being added, and that all sounds great except for a few issues. See, stability, because like during the Gilded Age of Swift, everything is controlled by Apple. It should be stable. It should be, oh, nope, it's not. Whoops. So I guess we didn't do that. All right, backward compatibility, at least we have that. Everything's maintained by Apple, right? Swift is closed source. Who cares? Oh no, it's not. See, Swift became open source. And while that was great for all of us now, it did cause some problems right as it happened. See, you can see there, you have Apache 2.0 license. That's like legal for do whatever you want with this. And what that means is that people are going to be using different versions of Swift and different versions of the Swift runtime, and we need to make sure that they're all able to work together, because at this point, Apple until now has been able to regulate what versions are in use. And what that means is that backwards compatibility is less of an issue. Here, now that Swift is open source, it's a pretty big issue. Having everyone on different versions means all the versions need to work together. Then again, there were some good things about this open sourcing. You get swift.org, you get the source code is now accessible to everyone. You get the Swift package manager. We're going to get a little bit more into that later. But for now, you just need to realize that it was sort of this bump in the road that eventually would lead to so much expansion for Swift, even if it made life harder for a brief period of time when it happens. Now we can do our little time travel sounds again, because we're going to be moving on to the present. Now, I'm not infringing on John's talk here. I swear, it's state of the language, not conference, it's state of the language. We're cool. All right, yeah. Moving on. Swift performance. At this point, you have Swift kind of being created with the intention of, I don't know if you guys have seen Talladega Nights, Ricky Bobby. All he says is, I want to go fast. And that's all that Swift is. Swift is an implementation that is so much faster than Objective-C. Just, it's fast, I think. I don't know if we have proof of that, but I think it's, oh. Okay, so we know that Swift is 8.4 times faster than Python, partially because Python is interpreted, not compiled. So that's going to slow it down. Stupid Python needs to be interpreted. Every time you want to run Python code, you need to figure out what it does all over again. It's not compiled into an easy format for the computer. It's easy for the developer, which slows it down. And these are great numbers, right? Like, they give you this whole complicated description about how they found it, depth first search algorithm, that 10,000 integers, graphs. There's so much information there. This has to be true. Wait, its source is Apple, huh? But they don't have a stake in this. We're good, right? These are actual numbers. Similarly, Swift versus Objective-C. Again, 2.6 times faster than Objective-C. We also don't have this just-in-time compilation, which is part of why it may be so much faster. With Swift, all of your code is compiled when you compile it. With Objective-C, you have the just-in-time compiler that leaves the uncompiled code to be prepared as soon as you're going to open your app. And that does slow you down. What that means is that Swift, by getting rid of this, has sort of a leg up to begin with. And that makes Swift this lightning fast. See, like, even their logo, it's on fire. It's super fast. It's like a phoenix. It's like Firefox, but with a bird instead of a fox. I mean, nobody really knows why they did that. That's kind of irrelevant. Only Chris Latner knows. Hail Chris Latner. Thank you. Much better that time. Thank you. But again, we still have this issue of Swift being dependent on Objective-C, because again, just because we open source does not mean that we somehow just eliminate all of our issues. So how do we solve this? Value type. Oh, wait, no. Everything that makes apps work is still the... All right, so everything that makes apps work is classes, but value types. So how are we going to do this? That is a really good question, huh? All right, so maybe we don't... See, because like we have this weird toxic relationship between Swift and Objective-C up until now. Swift has dreams. Swift has hopes. And Objective-C is just holding it back. Swift needs a push. And that push comes from Swift UI. So now we found our way to introduce those value types and speed up Swift and get us to fulfill those hopes and dreams that Swift had. Swift UI is this final brick in the wall between Swift and Objective-C. In other words, Swift UI is kind of that guy who like calls out Objective-C when it's all like drunk and being like, he's like, just dude, leave her alone. Like, let Swift be, you know? He gets in the way, and that's a good thing. Now that we have Swift UI everywhere, structs are going to kind of become Swift's new man, if you will. You know, Swift has a new preference for value types over reference types. Swift gets to be like my hero with the structs, and that's going to speed Swift up and make it better for all of us. Now, that's great. As you can see over here, everything in Swift UI is going to be struct-based, whether it's your previews, whether it's the views themselves. Everything in Swift UI is no longer focused on your reference types. Now we have this almost embracing of the value types, and that's going to, again, tie us all back to that initial issue of how do we handle memory. Again, Swift and Objective-C first started to break apart because of that memory issue. And now Swift is no longer even on the same wavelength of Objective-C. It's not even just the automatic reference counter anymore. Now we're just trying to find ways around the references entirely here. And now it's not to say that we're no longer using reference types at all. That is completely untrue. Swift UI has observable objects. There's a million classes that are still in here. However, we're now providing a different alternative that can work for creating views, whereas before we were completely tied to UIKit and those classes. And how does the performance of that work? Value types store in stack. That means that they are much, much faster to access. Whereas reference types were stored in heap, and then you had like links to them in the stack, the value types are simply stored in the stack to begin with, and that makes accessing them so much easier. Before, you had to record the reference counts, which again is going to take up more memory, more computation time, whereas with a value type, that is all irrelevant. You don't need to count how many of them there are, because for each value type, there is only one. And again, that kind of all plays to why Swift UI is pushing Swift away from Objective-C here. They just have this shared value of speed, and that's what we're looking at here. Swift UI, while on its own took a lot of reformatting, in the end, your apps will be faster in the future because there is less of a need to hold on to legacy code that could be slowing you down. While it may not be the best alternative right now, I believe that the future of Swift with Swift UI is going to be faster than the past. Again, you're not completely free of those reference types, unfortunately. Just recently, actors were implemented. That was, let's see, a year and a half ago. And on a basic level, you think this is just concurrency, but really no, it's not just concurrency. This is a push back towards those reference types. And again, there are projects where having these reference types is very important. There are projects where this is going to benefit you so much more than just trying to build all of your data trees just with value types. And again, I'm not going to go too in depth with this, but they're these magical things that essentially fix data structures. How they do that, don't worry about the implementation. But what they're going to do here is essentially make sure that whenever you're trying to access data from two different places, only one of those is going to be completed at a time to make sure that you're not changing something as you're reaching into it. You know, it's like if somebody offers you a bowl of candy and then as you reach in, somebody just switches it up to be like pigeon poop. Like, you don't want to reach in there anymore. Like, that's really a problem, you know? So as long as you know what you're doing before you do it, everything gets easier. And that's what we're doing here with this concurrency, is we are making sure that each action is completed one at a time. Somebody hands you a bowl of candy, you reach in, you take your candy, they can replace that candy with whatever they want now, you're out of there. It's not your problem. And that's great. Backward compatibility. That was our other little issue that we talked about before. But again, we have a bit of a solution here. Because when Swift open sourced, we introduced this whole new array of issues. All right, I'm not making puns like that. It's a whole new set of, a collection. You know what, just next slide. Anyway, we introduced ABI stability. Now the Swift runtime is included within the OS on device instead of within the app. The standard library, that is, more specifically, is going to be a part of each iOS that you download and updated independently of the app. The app, as you can kind of see on the left of that diagram there, is going to request access to the standard library, and then the device is going to fulfill that, whether it's using an older one, such as the one that the app is asking for, or a newer one, like that new red toolkit that's represented there. A little bit more detail into that. What we're doing here is we are essentially future-proofing Swift. We are making sure that whatever version your app is running on, all future versions will support that. So let's say I have an app that I compiled using some SDK that is Swift 5.0. However, I'm now on a device that is using Swift 5, Swift 5.1, Swift something in the future. Now, I'm not even going to say 6 because they kind of pulled this OSX thing where they went like 1, 2, 3, 4, 5, and then just 5.1, 5.2. Maybe in 10 years, we'll get up to Swift 6. Who knows? But in the meantime, it doesn't matter what it's called. Whatever newer versions of the runtime that you're trying to access, the older apps will now still be supported on those new devices thanks to ABI stability. In addition to that, we get some benefits with the app size. So before we had this redundancy, if you will. As you can kind of see on the diagram, those 3 apps are each using that same Swift standard library. And for a long time, each one of them held a copy of that library, there was no good reason to do that. Now, the standard library is on device, just like it was with Objective-C. And what you can see is that the app is now smaller, because before we had to hold 3 copies of that SDK and 3 copies of each app, or 1 copy of each app, 3 total apps. Now we still have the same apps. However, that standard library that we did hold 3 copies of, we now only hold 1. And that's just going to save us storage space on all of our devices, which again, can't hurt. In addition to storage, it's also going to reduce the app launch time. You see, the system library is now going to be prepared before app launch. So before, we needed to, every time I wanted to open an app, prepare the app, prepare its copy of the Swift standard library, and get that all ready to go. Now we are just now we are just preparing the app to launch, and we no longer need to worry about the library, which is prepared beforehand because it's running as part of the operating system. Now, before you had like Objective-C, this just-in-time compilation meant that every time that I wanted to open an app, I may be recompiling a piece of that code. That meant that it was really, really critical with Objective-C to make sure that as little launch was necessary to open each app. Now, with Swift, it was a little bit better. Since we don't have that just-in-time compilation, it was acceptable to say that we're going to prepare the toolkit each time we run it. However, now we're getting rid of that extra preparation, and even though it wasn't as huge of a cost savings as it was with Objective-C, it still is going to improve the launch time for every single app. And that only increases when you're no longer just using the standard library, but other libraries. With dynamic libraries, each other third-party library is going to act in a similar way to the Swift standard library. They are no longer a piece of that app binary. They are held as references. And what that means is that your app is going to essentially tell your device, hey, look and see if you have this library somewhere. And then my app, your app, and some other third person's app can all just hold references to the same library stored on device, instead of having to hold all of that extra information within my app binary, your app binary, that random third person's app binary that I just brought up before for no good reason. And now you have this static linker that is going to take the dynamic libraries that exist on device. They're going to take your source code, and they're going to put that together and make this one full complete app. And essentially your app on its own is no longer able to run without the device OS. What it is your app is a collection of references to products that exist on the device. And they tell this static linker, please fetch me these libraries if you have them. If not, I'll provide them. But if you have them, I'm not going to give you more of what you already have and waste space. I'm just going to take that already prepared library and use my app to interact with us. Now, we're not really going to be time traveling more right now. We're just going to kind of shift focus here and keep this section short. But again, it's not really time travel. It's really just a different place in the present that's like space travel. We can do that too. We're going to say that this is like the TARDIS or something. It's space travel, time travel, all of the above, just whatever. And here, we're going to start looking at the quirks of Swift. Now, Swift is a little bit different from many languages in good ways and bad ways. However, one of the less than awesome ways is that we have such a rich history behind it that it often leads to redundancies. So as you can see here, we have 4 different null types. All of them are nothing, and they're all just different flavors of nothing, if you will. See, null is because of our C ancestry. We had support for all of these pointers, and now that we're kind of getting rid of the need for pointers in Swift, you still have that null type where it's not commonly used, but if you're dealing with legacy code, you need access to the entire toolkit when you're dealing with pointers, and that means that you need your capital null. You have your lowercase nil. This is kind of our favorite little version of nothing. And I'm sure all of you are used to that. That's what you deal with when you have optional types, optional chaining, any sort of I don't know if this exists, and we use that all the time in Swift. Then we have capital nil. This capital nil, that's kind of the forgotten middle child, if you will. It's here. You don't use it much, but let's say you're dealing with a JSON decoder and you want to decode into a type that is nothing. Well, you can't use lowercase nil because that's a value for an object, not a class. And so that's when you use uppercase nil. Uppercase nil is great for the like 3 times you'll ever have to use it. Then there's ns null, which is when you don't have access to using little null. Let's say that I have something that I do need to submit a nothing type to, but it's not an optional. And we just decide, well, it's not an optional, well, screw that, we're putting nothing in there anyway because we want to do whatever we want. That's when you get to use ns null. And for a while, you used ns null dot lowercase null in Objective-C. That would give us 5 nulls. But in Swift, we wanted to simplify it down and make it easy. So instead of 5 nulls, we have 4 nulls. And now, so ns null just becomes its own type, and instead of using that singleton object that already exists, you just initialize it and you'd have ns null with the open and close parentheses. Another weird quirk of Swift to just look at is everything has ns. And again, that's something that many of you likely just take for granted. It's just, okay, it's there. It's always been like that. However, there's this whole history to it, and it all comes from Steve Jobs deciding to leave Apple. And again, it's just more legal stuff that gets thrown in here and messes up our lives as developers. It has to do with the licensing of Objective-C. So at one point, when Steve Jobs leaves, he decides, I want Objective-C, so I'm taking the baby with me, and he brings Objective-C. This is where you get AppKit and Foundation being developed by next step engineers instead of by their own original teams. And the next step engineers, being very self-centered themselves, they decide, well, we can't write code unless it has our name on it, so we're going to throw ns in front of everything and be selfish, because awesome. There's no good reason for it. However, nobody wants to change the names back later on because, again, developers are lazy. But also backwards compatibility. Nobody wants to rewrite all that legacy code. If it has ns before, we'll leave it with ns now because it's too much work to get rid of it. However, Swift, again, our developers have like a little bit of crazy in them, and we decide we're going to get rid of it anyway. And so that's how you have this transition now from ns string to string, ns data to data. So there is a like move to do it now, but again, it doesn't matter what you're doing, you're going to encounter some sort of legacy code that still involves ns. Whenever you want to use an attributed string, you still need to use ns attributed string. Why? Because Swift is not at the point where it has completely replaced everything within Objective-C. Again, Swift UI has tried to make its way around that, and it's in progress. And one day it may succeed at that, but where we are right now, there's still this weird tie between Swift and Objective-C. The last little quirk we're going to look at before we move on is protocols versus interfaces. So in most languages, including Java, you have these interfaces, and they are essentially protocols missing a few things. And you can kind of see over here, all that they do is allow you to define a type that conforms to a certain set of rules. And so the protocol is going to define those rules. And in this case, let's say the animal protocol says that you need to have a name and you need to be able to make a noise. Well, a dog definitely works with those rules. A dog makes a noise, a dog has a name. So you can create some sort of pet and say it has to be an animal. And then you can fill that pet with a dog. Why? Because dog fulfills all of the rules set forth by that animal protocol. But that doesn't really answer the question of why are we going to call these protocols when everyone else calls them interfaces? And the answer, again, goes back to Objective-C messing things up for us. So Objective-C header files, those .h1s, you're going to see that at interface absolutely everywhere. Every time you define a class, you are using that at interface keyword. So to call something new also an interface, now you have two things that are both kind of interfaces, and it gets all confusing for no good reason. And again, developers are also snobby. They take great pride in their work, even if it's not redefining the wheel. And in this case, we basically took what was already an interface, we added extensions, and we decided we can't call those interfaces anymore because they're way cooler because they have extensions. And so now, not being willing to associate with those non-extendable interfaces, we had to come up with a whole new name, and we were like protocol because that makes a lot more sense than interface to begin with. Now, moving on from those quirks, we are going to do a little bit more of space travel instead of that time travel. So you can start with your own noises, but in this case, we're going to keep them pretty specific. We're actually going to start doing some battle noises. because even in this room, there may be some divisiveness over this. There's a war going on, and that is a cross-platform war. We have a bunch of key players here, some of whom I will introduce to you. There is React Native. This is kind of Zuckerberg's metaverse option. You can see there's a lot of cross-platform stuff going on. You can read through those if you want. I'm not going to. There is also support for his very, very important operating system that runs his Quest VR services. If you want to create for that, go ahead. You can use React Native. The language of choice for React Native is going to be JavaScript. Now, I'm not really a fan of JavaScript just because of that dynamic typing. It's so much harder to keep track of what's going on. Luckily, you can use TypeScript if you're interested. Another one of those key players here is going to be Flutter. This was Google's entry. Again, it works with a lot of platforms that I'm not going to read because I don't care that much. It works using these widgets, but they're not really like the cool iOS widgets that we got a couple years back. These are like loser Google widgets, which are kind of irrelevant. Sorry, Google. Google made Dart, which is their alternative to Swift here, and it's like their like first cousin once removed on the Swift family tree, something like that. And Dart is going to be what powers Flutter here. And then again, just because they don't want to be left out, Microsoft decides we're doing ours too. Microsoft has Xamarin, and they use the .NET framework to build their own cross-platform UIs. Again, they go on a lot of platforms. You get the point. These are all cross-platform services. Their language of choice is C#, which is kind of like Swift's postman there. Like, it looks a lot like Swift, but they're not related. Like, we don't know why they look like that. But there are definitely similarities. Then you kind of have to pay attention here because you have this battle here, and the decision is not yet made as to who is going to win. There are pros to Swift. There are cons to Swift. Swift has a lot to offer, but it also does have drawbacks, you know? We have the advantage that comes with performance, native feature support, scalability. We get features that are added to the language immediately instead of having to wait and get them added to our separate cross-platform services. On the other hand, there are some cons too. There's an increase in the development time. They're harder to maintain with Swift than it is with the cross-platform services because a change that you make to your iOS app is not going to sync over to your Android app, and you have to deal with that yourself. Again, developers are lazy. We don't want to do that. That's a pretty big con. One nice thing about the cross-platform services is that in more recent years, there's been an increase in their support for native UI elements. And this one's not really a con of Swift as much as it's going back on our old pro and say, well, you're not the only one who can offer native feature support anymore. Going back to more of a retcon than a con. I know, that was a bad pun. Moving on. The pretty obvious one is that Swift doesn't have cross-platform support. Yet-ish. It kind of does. Moving on into the future. Noises. Thank you, Ed. The first thing up is, how do we settle that cross-platform war? How do we settle all of those differences that exist between Swift and our cross-platform enemies, if you will? The odds are kind of stacked against us. You have this David versus Goliath situation because the cross-platforms are dealing with several platforms. They can manage so much more, and Swift is kind of just up there on its own. And David's got his stone ready to throw, but then he doesn't throw it because that's dumb, and Swift like knows what it's doing and decides we're just going to join Goliath's team anyway and start doing cross-platform on our own because if you can't beat him, just join him. And in this case, be like David. David was smart. David decided to do cross-platform Swift on his own. Swift becoming cross-platform solves that last con by using that open source technology to extend Swift to other areas where Swift before was not able to reach. When it was an Apple technology, it didn't really make sense for Swift to be working on Windows, Linux. Now you have Swift extending everywhere, and it's been successfully integrated with Linux and Windows, and more work is being done. Right now there's a group called Scade, and Scade is working on introducing Swift to Android. They are currently in beta, although that beta was supposed to be wrapping up this month. We'll see how their progress goes in the next couple weeks and see if they get out of beta. But Scade allows you to use Swift to create apps on Xcode for both iOS and Android. In addition, they're implementing that Swift package manager that was first brought to fruition when Swift went open source. And it gives us the option to implement this Swift package manager that's fully open source on an Android app. Now, let's just look back at Objective-C and see if he was able to like pull his life together after all of those past events. Oh, no, he did not. Huh, okay. A whole lot of people do more extensive development in Swift, as you can see here. That's a pretty big number. Lots of people use Swift. Objective-C, on the other hand, not as many. In fact, 1.8 times more people are currently using Swift on a regular basis than they are Objective-C, and that is from the Stack Overflow yearly survey. On the other hand, the Popularity Programming Language Index has ranked Swift and Objective-C about evenly, and that is a somewhat new development that has happened in the past year to 2 years, where Swift is finally beating out Objective-C in terms of searches on Google for tutorials. Now, the PYPL kind of claims that they're using the best indicator there by saying more people are looking up Swift tutorials than Objective-C tutorials. That means Swift is more commonly used. I have to say there, I don't know about that, only because I think part of the reason that there are so many Objective-C tutorials still up there is because people don't know how to use it anymore. There are people who are now entering the industry who are not familiar with Objective-C. There are apps being built entirely with Swift that don't have Objective-C code in there. And so you have engineers who are now going into the industry and having to figure out the Objective-C stuff, and that's why they're looking up an increased number of tutorials. You see, before we had 1.8 times more people using Swift than Objective-C, and now to say that they're about the same on searches just shows that even the people using Objective-C, that's no longer their primary focus. They're still trying to figure out what they're doing. And now that we know that Swift is really leaving Objective-C in the past, what can Swift do in its future? First thing, machine learning. I mean, you can't blame Swift. Basically, everyone is just running towards machine learning at this point. Is it necessary? Sometimes yes, sometimes no. It's also a buzzword, so every company just says, we're going to do that because let's just do it. Who cares? It's a buzzword. It gets us money. But there are some good uses for machine learning, and Swift is just entering that industry and becoming increasingly applicable. TensorFlow recently added support for Swift with their Swift for TensorFlow toolkit. They added support for differentiable programming. As you can kind of see in that example up on the right, there's an example where you are using the dot product of two vectors as a function, and you can take the gradient of that, and as you can see over there, the gradient of that first function is going to give you 2x. And if you look up in the code, without having to do all of the derivation yourself, you can find the derivative of functions through this toolkit that is part of TensorFlow. And that was all added somewhat recently and will play a huge role in scientific Swift and in adding Swift into the machine learning world. In addition, you have Penguin and Swift RT, that's Swift runtime, that are really adding new levels of speed to Swift. You have them becoming used in science in a way that has never really been done before, because typically, scientifically, you're going to be using C++, C, things that are lightning fast and about as low overhead as possible. And now that we're adding Swift runtime to GPU and CPU, that is going to enable Swift to be used in a variety of new settings in a way that it hasn't been used before. In addition, you have parallel programming with Penguin, and that's just going to build on that. You can now run massive simulations using Swift on a GPU and get crazy advances in the speed up that you were going to not have before without the ability to use all of this parallel computation, solving scientific and physical problems using a language that we, at least in this room, are a lot more familiar with. In addition, we are going to add in server-side Swift. Now, there's a whole conference about this, server-side Swift. It's kind of a thing. You can go check it out later. But we're not at that conference. We're at this conference. So with that in mind, Swift will run on servers. That's about as basic as you need. However, you run into the issue of Swift running on servers. You want to reduce that overhead, and you're kind of pushing back towards the low-level programming in Swift, which we weren't really a fan of before. Again, going back to the biology, Swift can adapt. It'll make it work. So how is that being done? There are new products that are being brought to market. There's Vapor, which there were a couple talks on over the last 2 days, so I'm going to keep this brief because you already heard about it through them. There are a lot of advantages with this. Still, you're doing high-level memory management, and you still get that small memory footprint. So you're getting the best of both worlds without having to do so much extra work on your own as a developer. That's how you still have the automatic reference counting to deal with the memory optimization instead of you having to do it yourself. And now, just before we wrap up, I want to just give a special thanks to the 360 iDev team, Swift.org, Apple Developer, Techie Academy, NS Hipster, Stack Overflow, of course, who doesn't think that, and the Popularity of Programming Index, just for some nice statistics they gave. Now, just before we wrap up, I was going to wrap this up with just a question about Swift, that is, where to next? But after this morning, I think that the question just becomes even more relevant and not really just with relation to Swift. For years, iDev has been home for the iOS community. And I just want to say that the end of iDev is not the end of this community. So instead of asking where to next just for Swift, where to next for the Swift community? And I think it's up to all of us as a collective to answer that question. Thank you.